Today, 400 million miles from Earth, another Europa captures our imagination, not through myth, but through the tantalizing possibility that beneath its icy shell lies an ocean that might harbor the first life we discover beyond our own world. This frozen moon of Jupiter has become one of the most compelling destinations in our solar system, a place where science fiction meets scientific possibility. As we settle in for this journey together, we're going to explore every facet of this extraordinary world, from its discovery by Galileo on a winter night in 1610 to the ambitious missions being planned right now that might finally answer the question that keeps planetary scientists awake at night. Could there be something swimming in those dark waters beneath the ice? The story of Europa is really multiple stories woven together. The story of how we discovered it, the story of what we've learned about it, and perhaps most fascinating of all, the story of what might be waiting for us there. It's a narrative that spans 4 centuries of human curiosity and technological advancement, from the first crude telescopes to sophisticated spacecraft that have given us views of this moon that Galileo could never have imagined. What makes Europa so special among the more than 200 moons in our solar system is that combination of factors that makes it potentially habitable. We're not talking about a dead rock circling a planet. We're talking about a dynamic world with an ocean that might contain twice as much water as all of Earth's oceans combined. This ocean is kept liquid not by sunlight, which barely reaches this distant moon, but by the constant flexing and squeezing caused by Jupiter's immense gravity. Think about that for a moment. While you're lying here, comfortable and warm, there's an entire ocean, dark and mysterious, existing in perpetual night beneath a shell of ice that might be 15 miles thick in some places. In that ocean, conditions might be surprisingly similar to some of the most extreme environments on Earth, where we found life thriving against all odds. The cultural impact of Europa extends far beyond scientific circles. Science fiction writers have long been fascinated by this moon, imagining what might live beneath its ice. Arthur C. Clarke featured it prominently in his Space Odyssey series with the famous directive, "All these worlds are yours except Europa. Attempt no landing there." This fictional warning has become so embedded in popular culture that it's often referenced when discussing real missions to the moon. But Europa's influence on our culture goes deeper than fiction. It represents something fundamental about human nature, our desire to know if we're alone in the universe. Every image we receive from spacecraft, every piece of data we analyse, brings us closer to answering that profound question. Europa has become a symbol of possibility, a reminder that, even in our own cosmic backyard, there might be worlds as alien and mysterious as anything we could imagine. The scientific community's excitement about Europa is palpable. When scientists talk about this moon, their usual measured tones often give way to barely contained enthusiasm. Here is a world that checks so many boxes for potential habitability: liquid water, chemical energy sources, stability over billions of years, and the possibility of hydrothermal activity on the ocean floor. It's not just another interesting moon, it's potentially another place where life exists right now. As we begin this comprehensive exploration of Europa, we'll journey through time and space, starting with those first glimpses through primitive telescopes, and ending with the cutting-edge missions being designed to probe its deepest secrets. We'll examine the evidence that has built the case for that hidden ocean, understand the forces that keep it liquid, and explore what we know about the chemistry that might make life possible there. The story of Europa is also the story of human ingenuity and determination. Every mission to Jupiter has faced enormous challenges. The distance, the radiation, the complexity of orbital mechanics, the sheer cost and time involved. Yet we keep going back, each mission building on the last, each one revealing new mysteries even as it solves old ones. Tonight, as we explore Europa together, we're not just learning about a distant moon, we're contemplating our place in the universe, the possibility of life beyond Earth, and the incredible journey of discovery that has brought us to the point where we can seriously discuss sending submarines to an alien ocean. It's a story that connects us to our ancestors who first looked up at the night sky and wondered what those points of light might be, and to future generations who might one day know for certain whether Europa's ocean harbours life. The story of Europa's discovery begins on a cold January night in 1610, when Galileo Galilei turned his newly improved telescope toward Jupiter. What he saw would fundamentally change our understanding of the cosmos and our place within it. Through his modest instrument, with its 20 times magnification that would seem primitive by today's standards, Galileo observed what he initially thought were 3 fixed stars near Jupiter. They appeared to be arranged in a straight line through the planet, 1 to the west and 2 to the east. But Galileo, with the meticulous attention to detail that marked all his observations, noticed something peculiar the following night. These stars had moved. They were now arranged differently relative to Jupiter, and their positions couldn't be explained by Jupiter's own motion through the sky. This was extraordinary. Stars didn't move like this. Over the following nights, Galileo continued his observations, and on January 15th, he spotted a 4th object. These weren't stars at all. They were moons orbiting another planet. The discovery was revolutionary in ways that are difficult for us to fully appreciate today. For centuries, the prevailing view had been that everything in the heavens orbited Earth. The Church's doctrine supported this geocentric view, and challenging it was dangerous. Yet here was clear evidence that not everything revolved around our world. These 4 points of light, Io, Europa, Ganymede and Callisto, though Galileo wouldn't name them, were orbiting Jupiter. Galileo initially called them the Medicean stars, hoping to curry favour with his patron, Cosimo de' Medici. But it was Simon Marius, a German astronomer who claimed to have discovered them independently, who gave them the names we use today. Marius drew from mythology, naming them after Jupiter's lovers, a fitting choice given their eternal dance around the giant planet. Europa, the second of the 4, was named after the Phoenician princess whose beauty had captivated Zeus. In those early years, Europa was simply one of 4 dots of light that appeared and disappeared as they orbited Jupiter. Sometimes all 4 moons would be visible, sometimes fewer as they passed behind or in front of the planet. Galileo and other early observers meticulously tracked their movements, creating tables of their positions that would later prove invaluable for navigation and for testing theories of orbital motion. The precision of these early observations is remarkable when you consider the equipment being used. Galileo's telescope had a field of view about a quarter the width of the full moon, and chromatic aberration, the rainbow halos around bright objects, made precise observations challenging. Yet he and others managed to determine the orbital periods of the moons with surprising accuracy. Europa, they found, completed one orbit around Jupiter in about 3.5 days. As telescopes improved throughout the 17th and 18th centuries, astronomers began to notice more subtle details about Europa and its companions. They observed that the moons appeared to change in brightness as they orbited, suggesting they might always keep the same face toward Jupiter, just as our moon does with Earth. They noticed that the moons occasionally passed in front of one another, creating mutual events that could be timed precisely. One of the most significant early contributions to our understanding of Europa came from Ole Rømer, a Danish astronomer working at the Paris Observatory in the 1670s. Rømer was studying the timings of eclipses of Jupiter's moons, particularly Io, when he noticed something odd. The eclipses seemed to occur earlier when Earth was closer to Jupiter and later when Earth was farther away. This led him to a profound realization. Light had a finite speed. The delay was caused by the extra time it took light to travel the greater distance. Europa and its siblings had helped humanity discover one of the fundamental constants of the universe. By the late 18th century, William Herschel, famous for discovering Uranus, turned his powerful telescopes toward Jupiter's moons. Herschel was one of the first to attempt to measure the actual sizes of the moons, though his estimates were quite far off by modern standards. He thought Europa was much smaller than it actually is, but his work represented an important shift from simply tracking positions to trying to understand the physical nature of these distant worlds. The 19th century brought photography to astronomy, and with it, a new way of studying Europa. No longer did astronomers have to rely solely on what they could see and sketch in the moment. They could capture images and study them at leisure, compare observations from different nights, and share their findings with colleagues around the world. The first successful photograph of Jupiter and its moons was taken in 1892, showing them as tiny dots of light but proving that these distant worlds could be captured on photographic plates. As the 20th century dawned, Europa remained a mystery, a point of light whose true nature was completely unknown. Spectroscopy, the analysis of light to determine composition, was beginning to reveal the atmospheres of planets, but the moons of Jupiter were too small and faint for these early techniques. Europa was known to be the smallest of the 4 Galilean moons and to have a curiously high reflectivity, suggesting a surface quite different from our own moon, but beyond that it remained an enigma. The early 1900s saw improvements in both telescopes and techniques. Astronomers began to suspect that Europa's surface might be covered in ice, based on its high reflectivity or albedo. Ice would reflect much more sunlight than rock, explaining why Europa appeared brighter than expected for its size. But this was speculation based on indirect evidence. No telescope on Earth could resolve surface features on Europa. Edward Emerson, Barnard, one of the most gifted observational astronomers of his era, spent countless hours studying Jupiter's moons with the best telescopes available. In 1892 he discovered Amalthea, the first new moon of Jupiter found since Galileo's discoveries. While studying the Galilean moons, Barnard noted that Europa appeared distinctly different from the others, with a peculiar uniform brightness that suggested an unusually smooth surface. The 1920s and 30s brought new theoretical understanding of orbital dynamics that helped explain the complex dance of Jupiter's moons. It was discovered that Io, Europa, and Ganymede are locked in what's called a Laplace resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This wasn't just a curious coincidence, but a stable configuration that had profound implications for the moon's evolution and, as we would later learn, for Europa's potential habitability. By the 1950s, as the space age was about to begin, astronomers had determined Europa's basic orbital and physical parameters with reasonable accuracy. They knew it orbited Jupiter at a distance of about 417,000 miles, that it was roughly the size of Earth's moon, and that it had an unusually high reflectivity. Some speculated about an icy surface, but Europa remained essentially a mystery, a bright dot circling Jupiter, waiting for closer inspection. Gerard Kuiper, one of the most influential planetary scientists of the 20th century, made some of the first detailed spectroscopic observations of Europa in the 1950s. Using the McDonald Observatory in Texas, he detected what appeared to be water ice on Europa's surface. This was a crucial discovery, the first direct evidence of what Europa was made of, at least on its surface. But even Kuiper couldn't have imagined what lay beneath that ice. The 1960s brought a new urgency to planetary exploration as the space race accelerated. While public attention focused on the Moon and Mars, scientists were already planning missions to the outer solar system. Europa and the other Galilean moons were high-priority targets. These weren't just points of light anymore. They were worlds waiting to be explored. As computers became available for astronomical calculations, researchers could model the orbital dynamics of Jupiter's moons with unprecedented precision. They discovered subtle variations in the moon's orbits that provided clues about their internal structure. Europa's orbit, it turned out, was being affected not just by Jupiter's gravity, but by the gravitational pulls of the other moons, creating a complex interplay of forces that would prove crucial to understanding Europa's geology. The late 1960s and early 70s saw the last great era of ground-based discoveries about Europa before spacecraft would revolutionize our understanding. Improved infrared detectors allowed astronomers to measure the heat radiation from the Moon, providing clues about its surface temperature. They found that Europa's surface was incredibly cold, about -260 degrees Fahrenheit at the equator, and even colder at the poles. These observations also revealed something puzzling. Europa's surface temperature didn't vary as much as expected between day and night. This suggested that the surface material had unusual thermal properties, consistent with water ice, but still mysterious in many ways. Some scientists began to speculate that Europa might have a thin atmosphere, perhaps of water vapour, that could help moderate temperature extremes, but this remained highly uncertain. As the 1970s began, humanity stood on the brink of a new era of exploration. The Pioneer and Voyager missions were being planned, and Europa was about to transform from a dot of light into a world. The centuries of telescopic observation had given us the orbital mechanics, the basic size and mass, hints about surface composition, and tantalizing mysteries. But the real story of Europa was about to begin. Looking back at these early observations, we can see how each generation of astronomers built upon the work of their predecessors. From Galileo's first glimpse through his primitive telescope to the sophisticated spectroscopic studies of the mid-20th century, each observation added another piece to the puzzle. These patient observers, working with instruments that would seem impossibly crude today, laid the foundation for everything we now know about Europa. The dedication of these early astronomers is inspiring. They spent countless cold nights at their telescopes, carefully recording positions, timing events, making drawings. They had no idea that Europa might harbour an ocean, no concept that it might be one of the most promising places to search for life beyond Earth. To them, it was simply one of Jupiter's moons, a bright dot worthy of study because it was there, because understanding it might reveal something about the cosmos. Europa presents itself as one of the most intriguing bodies in our solar system, not just for what we can see, but for what lies hidden beneath its surface. With a diameter of 1,940 miles, Europa is slightly smaller than Earth's moon, making it the sixth largest moon in the solar system and the fourth largest of Jupiter's moons. But size alone doesn't tell Europa's story. It's the moon's unique composition and structure that make it so fascinating to planetary scientists. When we look at Europa from afar, the first thing that strikes observers is its brightness. The moon reflects about 64% of the sunlight that hits it, making it one of the most reflective bodies in the solar system. This high albedo immediately tells us something important about Europa's surface. It's covered in water ice, relatively pure and relatively young. Old dirty ice would be much darker, pocked with impact craters and covered in dust from space. Europa's brightness suggests a surface that's constantly being renewed. The mass of Europa, determined through careful observations of its gravitational effects on spacecraft and other moons, is about 48 billion trillion kilograms. When we combine this mass with Europa's volume, we get an average density of about 3.01 grams per cubic centimetre. This density is crucial because it tells us about Europa's internal composition. Pure water ice has a density of less than 1 gram per cubic centimetre, while rock is typically around 3 grams per cubic centimetre or higher. Europa's intermediate density suggests it's a combination of both rock and ice, what planetary scientists call a differentiated body. Differentiation is a fundamental process in planetary formation. When a body has enough mass and heat, gravity causes heavier materials to sink toward the centre, while lighter materials rise to the surface. In Europa's case, this means a rocky, metallic core surrounded by a layer of water in some form. But the story of Europa's structure is far more complex and interesting than this simple description suggests. Let's start from the inside and work our way outward. At Europa's heart lies a core of rock and metal, probably similar in composition to terrestrial meteorites. This core is estimated to be about 850 to 900 miles in radius, making up a significant portion of Europa's interior. The core isn't just a solid lump of rock, it's likely layered itself, with the densest metallic components at the very centre and silicate rock surrounding them. The temperature at Europa's core is a subject of ongoing scientific debate. Models suggest it could be anywhere from about 2,000 to 3,000 degrees Fahrenheit, hot enough to maintain some level of geological activity, but not nearly as hot as Earth's core. This heat comes from several sources. The original heat from Europa's formation billions of years ago, the decay of radioactive elements within the rocky material, and possibly most importantly, tidal heating from Jupiter's gravity. Surrounding this rocky core is where Europa gets really interesting. A layer of water approximately 60 to 100 miles thick. But this isn't just a simple shell of ice. The evidence strongly suggests that this water layer is differentiated into at least two parts, a liquid ocean and an ice shell. The ocean, sandwiched between the rocky core below and the ice above, is one of the most extraordinary features in our solar system. The ice shell that covers Europa's ocean is estimated to be between 15 and 25 miles thick, though this thickness likely varies across the moon's surface. This isn't ordinary ice like you might find in your freezer. Under the extreme conditions of Europa, intense cold at the surface, pressure from overlying layers, and stress from Jupiter's tidal forces, water ice behaves in complex ways. It can flow like a very slow glacier, crack and shift like Earth's tectonic plates, and possibly even convect, with warmer ice rising and cooler ice sinking. The surface ice on Europa exhibits several different phases or crystal structures depending on temperature and pressure. At the very surface, where temperatures hover around minus 260 degrees Fahrenheit at the equator and minus 370 degrees at the poles, we find what's called ice EH, the same hexagonal crystal structure of normal ice on Earth. But deeper down, as pressure increases, the ice might transform into other phases like ice 2 or ice 3, which have different crystal structures and properties. One of the most remarkable aspects of Europa's surface composition is its apparent purity. Spectroscopic observations show that the ice is predominantly water ice with very few contaminants. However, there are intriguing traces of non-ice materials, particularly in Europa's network of ridges and cracks. These materials appear reddish-brown in colour and are thought to be salts and possibly organic compounds that have welled up from the ocean below. The presence of these materials on the surface is one of our best pieces of evidence for communication between the ocean and the surface. The composition of these non-ice materials is particularly fascinating. Spectroscopic analysis has identified what appears to be magnesium sulfate, similar to Epsom salts on Earth. There's also evidence for sodium chloride, ordinary table salt, which would indicate that Europa's ocean is salty like Earth's oceans. Some observations suggest the presence of hydrogen peroxide and other compounds created by the interaction of water ice with Jupiter's intense radiation environment. Speaking of radiation, we can't discuss Europa's composition without considering the profound effects of Jupiter's magnetosphere. Europa orbits within Jupiter's powerful magnetic field in a region bombarded by high-energy particles. This radiation is so intense that it would deliver a lethal dose to an unprotected human in just a matter of minutes. But this same radiation drives fascinating chemistry on Europa's surface. When high-energy particles strike water ice, they break apart the water molecules, creating hydrogen and oxygen. The hydrogen, being light, escapes to space relatively easily, while the heavier oxygen can recombine in various ways. Some forms molecular oxygen, creating a thin atmosphere around Europa. Some combines with sulfur from volcanic Io to create sulfur dioxide and other compounds. This radiation-driven chemistry creates a dynamic surface environment where the ice is constantly being broken down and reformed. The radiation also creates what scientists call a radiolytic layer on Europa's surface, a zone where the ice has been chemically altered by radiation. This layer might be only a few inches to a few feet thick, but it represents a unique chemical environment that doesn't exist anywhere on Earth. Some scientists have suggested that this radiolytic zone could be an energy source for potential life, providing chemical disequilibrium that organisms could exploit. Europa's thin atmosphere, or exosphere, is another important aspect of its composition. This atmosphere is incredibly tenuous. If you were standing on Europa's surface, it would seem like a vacuum. The atmosphere consists primarily of molecular oxygen, with a surface pressure about 100 billion times less than Earth's. This oxygen comes from the breakdown of water ice by radiation, as mentioned earlier. There are also trace amounts of water vapour, particularly over warmer regions or where plumes might be venting from below. The discovery of potential water vapour plumes erupting from Europa's surface has added another dimension to our understanding of its composition. These plumes, if confirmed, would be carrying material directly from the subsurface ocean into space. Analysis of this material could tell us about the ocean's composition without having to drill through miles of ice. The plumes appear to contain water vapour, of course, but possibly also salts, organic molecules, and other compounds from the ocean. Europa's magnetic field, or rather its induced magnetic field, provides crucial evidence about its internal composition. Europa doesn't generate its own magnetic field like Earth does, but as it moves through Jupiter's magnetic field, it develops an induced field. The characteristics of this induced field tell us that there must be a conducting layer within Europa, and the best candidate for this conducting layer is a salty ocean. The strength and pattern of the induced field even give us clues about the ocean's depth and salinity. The question of Europa's ocean composition is one of the most important in astrobiology. Based on models and indirect evidence, scientists believe the ocean is likely salty, with a composition perhaps not too different from Earth's oceans. The salts probably include magnesium sulfate, sodium chloride, and possibly other compounds. The pH of the ocean, whether it's acidic, neutral, or basic, is unknown but crucial for understanding its habitability. If there's hydrothermal activity on Europa's ocean floor, where water interacts with hot rock, it could be adding all sorts of minerals and compounds to the ocean. These might include iron, sulfur compounds, and possibly even simple organic molecules. This chemistry at the rock-water interface could be similar to deep-sea hydrothermal vents on Earth, which support thriving ecosystems independent of sunlight. The temperature profile through Europa's interior is another crucial aspect of its physical characteristics. At the surface, temperatures are brutally cold, never rising above about -220 degrees Fahrenheit, even in direct sunlight. But as you go deeper, temperatures rise. The ice warms gradually until, at the ice-ocean interface, it reaches the melting point of water under those pressure conditions, probably around 28 degrees Fahrenheit, slightly below the freezing point of pure water due to the presence of salts. In the ocean itself, temperatures are thought to range from about 28 degrees Fahrenheit near the ice ceiling to perhaps 40 degrees, or warmer, near the rocky floor, especially if there's hydrothermal activity. These temperatures are cold by Earth standards, but perfectly suitable for liquid water under pressure, and well within the range where life thrives on Earth. The pressure in Europa's ocean is another extreme factor. At the top of the ocean, beneath perhaps 15 miles of ice, the pressure would be about 1,300 times Earth's atmospheric pressure, similar to the deepest trenches in Earth's oceans. At the bottom of the ocean, the pressure could be even greater. Life on Earth has been found thriving at such pressures, so this alone wouldn't preclude the possibility of life in Europa's ocean. Europa's bulk composition also tells us about its formation and history. The Moon probably formed from the disk of gas and dust that surrounded Jupiter in its early days, similar to how planets formed around the Sun. The composition suggests Europa formed in a region where both rock and ice were available, probably beyond Jupiter's snow line, where temperatures were cold enough for water to condense as ice. The ratio of rock to ice in Europa, roughly 50-50 by volume, though the rock makes up about 90% of the mass due to its higher density, suggests it formed in a specific region of the Jovian system. If it had formed closer to Jupiter, it would have less ice. If it had formed farther out, it would have more ice and possibly other volatile compounds like ammonia or methane. Trace elements and isotope ratios in Europa's composition, though difficult to measure from a distance, could tell us even more about its history. For example, the ratio of different oxygen isotopes could reveal whether Europa's water came from the same source as Earth's water, or from a different population of comets or asteroids. The presence of certain radioactive isotopes and their decay products could help date different features on Europa's surface. Beneath Europa's frozen surface lies one of the most extraordinary features in our solar system, a vast dark ocean that has existed for billions of years. This hidden sea contains more than twice the volume of all Earth's oceans combined, despite Europa being significantly smaller than our planet. The existence of this ocean transforms Europa from just another moon into a world that might harbour life, making it one of the most important destinations for future exploration. The evidence for Europa's subsurface ocean has been building for decades, accumulating from multiple independent lines of investigation that all point to the same remarkable conclusion. The story of how we discovered this hidden ocean is a testament to human ingenuity and the power of remote observation, piecing together clues from spacecraft data, laboratory experiments, and theoretical models to reveal a world we cannot directly see. The first hints of something unusual beneath Europa's surface came from the Voyager missions in 1979. When Voyager 1 and Voyager 2 flew past Jupiter and its moons, they sent back images that showed Europa's surface was unlike anything else in the solar system. Instead of being heavily cratered like most moons, Europa's surface was smooth and bright, crisscrossed with a complex network of ridges and cracks. The lack of large craters immediately told scientists that Europa's surface was young, perhaps only tens of millions of years old instead of billions. But it was the nature of those cracks and ridges that really caught scientists' attention. They looked remarkably similar to features found in Earth's polar ice caps, where ice floats on water. The patterns suggested that Europa's ice shell might be floating on something liquid, and that this ice shell was being stressed and fractured by some ongoing process. Some scientists began to speculate about the possibility of a subsurface ocean, but the evidence was still circumstantial. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided the smoking gun evidence for Europa's ocean. One of Galileo's key instruments was a magnetometer, designed to study Jupiter's powerful magnetic field. As the spacecraft flew past Europa, the magnetometer detected something unexpected. Europa was slightly modifying Jupiter's magnetic field in its vicinity, as if the Moon had its own magnetic field. But the characteristics of this magnetic signature were peculiar. The field wasn't constant like Earth's magnetic field, which is generated by our planet's molten iron core. Instead, Europa's magnetic field varied in strength and direction as the Moon orbited Jupiter, always opposing the changing direction of Jupiter's field at Europa's location. This is exactly what you would expect from an induced magnetic field, a field created in a conducting material when it moves through an external magnetic field. For a magnetic field to be induced in Europa, there had to be a layer of electrically conducting material somewhere within the Moon. Ice doesn't conduct electricity, and neither does rock under normal conditions. But saltwater does. The magnetic field data could be perfectly explained if Europa had a layer of salty water beneath its ice shell. Moreover, the strength of the induced field gave scientists information about the depth and extent of this conducting layer. It had to be global, it had to be at least several miles thick, and it had to be within about 60 miles of the surface. This magnetic evidence for an ocean was supported by gravitational measurements. As Galileo flew past Europa at different distances and angles, slight variations in the spacecraft's trajectory revealed details about Europa's internal structure. These measurements confirmed that Europa is differentiated, with a dense core and a lighter outer layer. But more importantly, they suggested that the outer layer of water wasn't entirely frozen. There had to be a liquid layer to explain the observed mass distribution. The surface features of Europa provide additional compelling evidence for an ocean. The ridges that crisscross Europa's surface often show a characteristic pattern, a central crack flanked by raised ridges on either side. This pattern is consistent with water or warm ice welling up from below, pushing the surface ice apart and creating new terrain. It's remarkably similar to the process of seafloor spreading on Earth, where new ocean crust is created at mid-ocean ridges. Even more intriguing are regions called chaos terrain, where the surface appears to have been broken into blocks that have shifted and rotated before refreezing in place. These areas look exactly like what you might expect if sections of ice were floating on liquid water, breaking apart and jostling against each other like ice flows in Earth's Arctic Ocean. Some of these ice blocks appear to have rotated by tens of degrees from their original positions, which would be nearly impossible if they were attached to solid ice all the way down. The pattern of Europa's fractures also tells us about the ocean. Many of the cracks and ridges follow curved paths that match what we would expect from tidal stresses if the ice shell were decoupled from the rocky interior by a liquid layer. If Europa were frozen solid all the way through, the pattern of fractures would be different. Computer models show that the observed pattern of lineaments, as these linear features are called, can only be explained if the ice shell can slip and rotate relative to the interior, which requires a liquid layer between them. Temperature modelling provides another line of evidence. Europa's surface is incredibly cold, but the interior is heated by tidal forces. As Europa orbits Jupiter, the giant planet's gravity stretches and squeezes the Moon, generating heat through friction. This tidal heating is most efficient in a Moon that has a liquid layer, because liquids can deform more easily than solids. Calculations show that tidal heating in Europa could generate enough heat to maintain a liquid ocean for billions of years, especially when combined with radioactive heating from the rocky core. The discovery of potential plumes of water vapour erupting from Europa's surface has provided some of the most exciting recent evidence for the ocean. These plumes, first detected by the Hubble Space Telescope in 2012 and observed several times since, appear to shoot water vapour and possibly other materials up to 120 miles above Europa's surface. If confirmed, these plumes would be direct evidence of liquid water beneath the surface, and they would provide a way to sample the ocean's composition without having to drill through the ice. The plumes appear to be intermittent, possibly triggered by the tidal stresses Europa experiences as it orbits Jupiter. When Europa is farthest from Jupiter in its slightly elliptical orbit, the tidal stresses are greatest, potentially opening cracks that allow water to escape. This correlation between plume activity and orbital position strengthens the case that the plumes are real and that they're connected to a subsurface ocean. But what keeps this ocean liquid? After all, Europa is 5 times farther from the Sun than Earth is, receiving only about 4% as much solar energy. The surface temperature never rises above minus 220 degrees Fahrenheit, cold enough to freeze water instantly. The answer lies in the unique gravitational environment of the Jovian system and the remarkable phenomenon of tidal heating. Europa is locked in an orbital resonance with 2 other large moons of Jupiter, Io and Ganymede. For every 4 orbits Io completes, Europa completes exactly 2 and Ganymede completes 1. This resonance means that the 3 moons regularly line up in the same configuration, creating a repeating pattern of gravitational pulls. These gravitational interactions prevent Europa's orbit from becoming perfectly circular, maintaining a slight eccentricity that is crucial for tidal heating. As Europa follows its slightly elliptical orbit, it experiences varying levels of tidal force from Jupiter. When Europa is closest to Jupiter, the tidal bulge, the deformation of the Moon caused by Jupiter's gravity, is larger. When Europa is farthest from Jupiter, the bulge is smaller. This constant flexing of Europa's shape creates friction within the Moon, generating heat. It's like repeatedly bending a paperclip. Eventually, the paperclip gets warm from the internal friction. The amount of tidal heating depends on the internal structure of Europa. A completely solid moon wouldn't flex as much and wouldn't generate as much heat. A moon with a liquid layer can deform more easily, generating more heat. This creates an interesting feedback loop. The ocean allows for more tidal heating, which helps keep the ocean liquid. Current estimates suggest that tidal heating generates about 10 to 100 terawatts of heat in Europa. For comparison, Earth's total heat flow from its interior is about 47 terawatts. This means that tiny Europa, with less than 1% of Earth's mass, might be generating a comparable amount of internal heat. This heat flow is more than enough to maintain a liquid ocean, and it might even drive geological activity on the ocean floor. The depth and volume of Europa's ocean are subjects of ongoing research and some uncertainty. Most models suggest the ocean is between 40 and 100 miles deep, with 60 miles being a commonly cited estimate. Given Europa's size, this translates to a global ocean volume of about twice that of Earth's oceans. This vast amount of liquid water has existed for most of Europa's history, providing a stable environment where chemical reactions could occur and potentially life could evolve. The ocean's chemistry is crucial for understanding its potential habitability. Based on the surface composition and models of Europa's interior, scientists believe the ocean is salty, with dissolved salts including magnesium sulfate and sodium chloride. The salinity is important for several reasons. First, salt lowers the freezing point of water, helping to keep the ocean liquid. Second, salts make the water electrically conductive, explaining the magnetic field observations. Third, the specific types of salts present could tell us about the chemical reactions occurring between the ocean and the rocky seafloor. The pH of Europa's ocean, whether it's acidic, neutral, or basic, is unknown but critically important. Earth life as we know it can tolerate a wide range of pH values, but extreme acidity or alkalinity could make the ocean inhospitable. Models suggest that Europa's ocean might be slightly acidic to neutral, depending on the amount of carbon dioxide and other compounds dissolved in it. If there's significant interaction between the ocean and the rocky core, buffering reactions could help maintain a relatively stable pH over geological time. The pressure at the bottom of Europa's ocean would be immense, perhaps 1,500 times Earth's atmospheric pressure or more. This is comparable to the deepest parts of Earth's oceans, where we found thriving ecosystems. The pressure would affect the chemistry of the water, the behaviour of dissolved gases, and the properties of any ice that might form at depth. Under such extreme pressure, water ice can form even at temperatures above the normal freezing point, creating exotic high-pressure ice phases. One of the most exciting possibilities is that Europa's ocean floor might host hydrothermal vents, similar to those found on Earth's ocean floor. If the rocky mantle is still geologically active, heated by radioactive decay and tidal forces, it could drive hydrothermal circulation. Water would seep into cracks in the rock, get heated, and rise back up, carrying dissolved minerals and gases. These hydrothermal systems could provide chemical energy that life could exploit, just as they do on Earth. The evidence for possible hydrothermal activity is indirect but intriguing. The detection of what might be clay minerals on Europa's surface suggests that water-rock interactions have occurred. The relatively young surface age implies ongoing geological activity, and models of Europa's thermal evolution suggest that the rocky interior should still be warm enough to drive hydrothermal circulation, at least in some regions. The circulation patterns within Europa's ocean are another fascinating aspect of this hidden world. Unlike Earth's oceans, which are driven primarily by wind and differences in temperature and salinity at the surface, Europa's ocean would be driven by different forces. Heat from the rocky core would create convection currents, with warmer water rising and cooler water sinking. The rotation of Europa and the tidal forces from Jupiter would also influence ocean currents. Computer simulations suggest that Europa's ocean might have a complex pattern of circulation, possibly including the equivalent of ocean gyres and currents. These currents would be important for distributing heat, chemicals, and potentially nutrients throughout the ocean. They could transport material from hydrothermal vents on the ocean floor up toward the ice ceiling and carry surface materials that have been incorporated into the ocean down to the depths. The interface between the ocean and the ice shell above is a particularly interesting environment. Here, the water would be at its coldest, just at the freezing point. Ice would be constantly melting and refreezing, potentially creating a slushy transition zone. This interface might be rough and complex, with ice stalactites hanging down and pockets of water extending up into the ice. If there are salts in the ocean, they would be excluded from the ice as it freezes, creating extra salty brine channels and pockets within the lower ice shell. Some scientists have proposed that these brine pockets and channels could be habitable environments in their own right. On Earth, we've found microorganisms living in brine channels within sea ice, surviving at temperatures well below the freezing point of pure water. Similar environments might exist in Europa's ice shell, potentially extending the habitable zone beyond just the ocean itself. The possibility of seafloor volcanism on Europa adds another dimension to this hidden ocean world. While we have no direct evidence of volcanic activity on the ocean floor, it's plausible given what we know about Europa's interior. The rocky mantle is likely similar in composition to terrestrial planets, containing radioactive elements that generate heat as they decay. Combined with tidal heating, this could be enough to cause partial melting and volcanism. If submarine volcanoes do exist on Europa, they would dramatically affect the local ocean environment. They would inject heat, gases, and minerals directly into the ocean. Volcanic gases like hydrogen sulfide, methane, and hydrogen could provide chemical energy for potential life forms. The minerals would affect ocean chemistry and could precipitate out to form seafloor deposits. Over billions of years, these processes could have significantly altered the composition of Europa's ocean. The darkness of Europa's ocean is absolute. Sunlight cannot penetrate through 15 or more miles of ice, so the ocean exists in perpetual night. This has profound implications for any potential life. Without sunlight, photosynthesis, as we know it, would be impossible. Any ecosystem would have to be based on chemosynthesis, deriving energy from chemical reactions rather than light. But darkness doesn't mean lifelessness. Earth's deep oceans are also dark, yet they teem with life. At hydrothermal vents, entire ecosystems thrive in complete darkness, based on bacteria that derive energy from chemical reactions involving hydrogen sulfide and other compounds. If similar chemical energy sources exist in Europa's ocean, they could support analogous ecosystems. The stability of Europa's ocean over geological time is remarkable. Based on models of Europa's thermal evolution and orbital dynamics, the ocean has probably existed for most of the Moon's 4.5 billion year history. This long-term stability is crucial for the potential development of life. On Earth, life appeared relatively quickly once conditions were suitable, perhaps within a few 100 million years. Europa's ocean has had 10 times longer than that. The exchange of material between the ocean and the surface is another important aspect of Europa's ocean system. While the thick ice shell acts as a barrier, it's not completely impermeable. Ridges and chaos regions suggest that ocean material has reached the surface in the geologically recent past. Impact craters might occasionally punch through thin sections of the ice shell, allowing direct communication between the ocean and surface. And the potential plumes provide a current-day mechanism for ocean material to reach the surface and even escape to space. This exchange is important for several reasons. It means that we might be able to learn about the ocean's composition by studying the surface. It also means that surface materials, including organic compounds created by radiation chemistry, could potentially reach the ocean. And it suggests that the ocean is not a completely closed system, but part of a larger, dynamic world. The question of stratification in Europa's ocean is particularly intriguing. Earth's oceans are stratified with distinct layers of different temperature and salinity. Europa's ocean might also be stratified, perhaps with a fresher layer near the ice ceiling where salts are excluded during freezing, and a saltier layer near the bottom. Or there might be temperature stratification, with warmer water near the seafloor if there's significant heat flow from below. Recent research has suggested that Europa's ocean might contain Epsom salt rather than table salt as its dominant dissolved compound. This has important implications for the ocean's properties and potential habitability. Epsom salt oceans would be more acidic than table salt oceans, potentially affecting what kinds of life could survive there. The specific salt composition would also affect the ocean's freezing point, density, and circulation patterns. The possibility of ocean pockets or lakes within Europa's ice shell adds another layer of complexity to this hidden water world. Radar data and surface features suggest that there might be bodies of liquid water entirely enclosed within the ice shell, separated from the main ocean. These lakes could form from local heating, salt concentration, or other processes. They would represent unique environments, potentially with different chemistry than the main ocean. Europa's surface tells a story written in ice, a narrative of geological processes unlike anything we see on Earth, yet hauntingly familiar in some ways. When we look at Europa through the eyes of our spacecraft, we see a world that has been shaped by forces, both alien and recognizable. Tidal stresses that crack the ice in predictable patterns, chaos regions where the surface has been disrupted and reformed, and ridges that speak of material welling up from below. This icy shell, perhaps the most geologically young surface in the outer solar system, is a dynamic canvas that records the ongoing interaction between Europa's hidden ocean and the hostile environment of space. The first thing that strikes any observer about Europa's surface is its remarkable smoothness and brightness. From a distance, Europa looks like a cracked marble, white with reddish-brown veins running through it. The surface reflects about 64% of the sunlight that hits it, making it one of the brightest objects in the solar system. This high reflectivity immediately tells us that the surface is dominated by relatively pure water ice, constantly renewed and refreshed through geological processes that prevent the accumulation of dark, dusty material that covers most other airless bodies. The lack of large impact craters on Europa's surface was one of the first clues that something unusual was happening there. While other moons like Callisto and Ganymede are heavily cratered, recording billions of years of bombardment, Europa shows very few craters larger than a few miles across. The ones that do exist often look degraded and modified, as if the ice has flowed and deformed to partially erase them. This suggests that Europa's surface is incredibly young in geological terms, perhaps only 40 to 90 million years old on average, though some regions might be even younger. The most prominent features on Europa's surface are the long linear cracks and ridges that crisscross the moon in a complex pattern that has been likened to the lines on a cracked eggshell. These features can stretch for thousands of miles, cutting across other terrain and each other in a way that allows scientists to determine their relative ages. The younger lineae cut across older ones, creating a complex record of stress and fracturing that has accumulated over millions of years. These ridges come in various forms, each telling us something different about the processes that created them. Double ridges are the most common type, consisting of two raised ridges separated by a central trough. These features can be remarkably consistent, maintaining the same width and height for hundreds of miles. The leading theory for their formation involves a crack in the ice that opens and closes repeatedly due to tidal stresses. Each time the crack opens, water or warm ice from below fills the gap. When it closes and refreezes, the expanded material is pushed up, gradually building the ridges on either side. Some ridges show evidence of what scientists call spreading center behavior, similar to mid-ocean ridges on Earth, where new seafloor is created. The patterns of parallel bands on either side of some ridges match up like a jigsaw puzzle, suggesting that the ice has been pulling apart, and new material has been filling the gap. This is extraordinary when you think about it. We're seeing a form of plate tectonics, but in ice rather than rock, driven by tidal forces rather than mantle convection. Complex ridged plains cover vast areas of Europa's surface, representing regions where multiple generations of ridges have formed, intersected, and been modified over time. These plains tell a story of continuous geological activity, with new ridges constantly forming, while older ones are gradually erased or overprinted. The sheer complexity of these regions makes them difficult to interpret, but they clearly indicate that Europa's surface has been geologically active for a very long time. Perhaps the most intriguing features on Europa's surface are the chaos regions, areas where the organised pattern of ridges gives way to a jumbled mess of ice blocks, hummocks, and irregular terrain. These regions, with evocative names like Connemara Chaos and Thera Macula, look exactly like what you might expect if sections of the ice shell had melted or become mobile, allowing ice blocks to rotate and shift before refreezing in place. The formation of chaos terrain is still debated among scientists, but most theories involve some form of communication between the ocean and the surface. One possibility is that warm plumes of water rise from the ocean, melting or softening the ice from below. Another theory suggests that lakes of liquid water within the ice shell might occasionally break through to the surface. Whatever the mechanism, chaos regions clearly represent places where the normal structure of the ice shell has been disrupted by forces from below. Within chaos regions, we can see ice blocks that have clearly moved from their original positions. Some have rotated by tens of degrees, while others have tilted or shifted laterally. The matrix material between these blocks often appears darker and redder than the surrounding ice, possibly containing salts or other materials from the ocean below. This makes chaos regions particularly interesting targets for future missions, as they might provide windows into the composition of the subsurface ocean. Europa's surface also features large-scale patterns that reveal the influence of tidal forces. The orientation of many ridges and cracks follows predictable patterns based on the stresses Europa experiences as it orbits Jupiter. These tidal stresses change in a complex way due to Europa's slightly eccentric orbit and its synchronous rotation, always keeping the same face toward Jupiter. Scientists have developed sophisticated models to predict where and when cracks should form based on these tidal stresses. Remarkably, many of Europa's actual features match these predictions, confirming that tidal forces play a major role in shaping the surface. However, some features don't match the predicted patterns, suggesting that other processes, perhaps related to the ice shell's thickness variations or ocean currents below, also influence surface geology. The surface of Europa also shows evidence of what might be cryovolcanism, volcanism involving water and ice rather than molten rock. Smooth plains that appear to have flooded older terrain suggest that liquid water, or warm, mobile ice, has erupted onto the surface and frozen. Some dome-like features might be ice volcanoes or cryovolcanoes, where warm ice has pushed up from below. The discovery of potential active plumes on Europa represents the most dramatic form of cryovolcanism. These plumes, if confirmed, would be erupting water vapour and possibly ice particles high above the surface, similar to the geysers on Saturn's moon Enceladus. The plumes appear to originate from relatively warm regions on Europa's surface, particularly near the equator, and might be associated with recent geological activity. Impact craters on Europa, while rare, provide valuable information about the ice shell's structure and properties. The largest confirmed impact crater on Europa is Puil, about 25 miles in diameter. Puil is remarkably fresh-looking, with bright white ejecta rays extending hundreds of miles from the impact site. The morphology of Europa's craters is unusual. Many show evidence of flow and relaxation, as if the ice has gradually sagged and flowed to partially fill them in. Multi-ring impact structures on Europa are particularly interesting. When a large impact occurs, it creates not just a single crater, but a series of concentric rings, like ripples in a pond. The spacing and characteristics of these rings provide information about the ice shell's thickness and the presence of the ocean below. Some impacts might have been large enough to punch completely through the ice shell, temporarily exposing the ocean to space. The colour variations on Europa's surface provide clues about composition and processes. The base colour is white from pure water ice, but there are extensive regions of reddish-brown material, particularly along ridges and in chaos terrain. This non-ice material is thought to be salts and possibly organic compounds that have been altered by Jupiter's intense radiation. The radiation breaks down the molecules and creates new compounds, including sulfur compounds that give the characteristic reddish colour. Some of the most intriguing coloured features on Europa are dark spots and patches that might represent relatively recent exposure of subsurface material. These features, called maculae, often appear in association with chaos terrain or other disrupted regions. They might represent places where ocean material has recently reached the surface, providing potential windows into the ocean's composition. The small-scale texture of Europa's surface, as revealed by our highest resolution images, shows a complex landscape of pits, grooves, and rough terrain at scales of tens of feet. This texture is thought to result from a process called sublimation erosion, where ice transforms directly from solid to vapour in the vacuum of space. Over time, this process creates a rough, pitted surface texture that we call penitentes, after similar features found in high altitude. Snowfields on Earth, Europa's polar regions show some distinct differences from the equatorial areas. The poles appear to have a different texture and possibly composition, with some scientists suggesting that material from the radiation-produced atmosphere might preferentially accumulate there. The polar regions also show different patterns of fracturing, influenced by the unique stress patterns at high latitudes. Tectonic processes on Europa operate in ways both similar to and different from Earth. Like Earth, Europa appears to have regions where new surface is created and old surface is destroyed or modified. But unlike Earth's plate tectonics, which involves rigid plates of rock moving over a plastic mantle, Europa's tectonics involves ice plates potentially floating on liquid water. This creates a unique form of ice tectonics that we're only beginning to understand. The rate of resurfacing on Europa is a critical question for understanding both its geology and potential habitability. If the surface is being renewed very rapidly, it means there's frequent communication between the ocean and surface. If resurfacing is slower, the ice shell might be thicker and more stable. Current estimates suggest that the average surface age of 40 to 90 million years represents a balance between impact cratering and resurfacing processes. Seasonal variations on Europa, while subtle due to Jupiter's small axial tilt, might influence surface processes. As Europa orbits Jupiter, which takes about 12 Earth years to orbit the Sun, different regions experience slight variations in solar heating. While these variations are tiny compared to the tidal heating that dominates Europa's energy budget, they might influence where and when certain surface processes occur. The dance that Europa performs around Jupiter is far more than a simple ellipse in space. It's a complex choreography involving gravitational resonances, tidal forces, and orbital dynamics that fundamentally shape every aspect of this remarkable moon. Understanding Europa's orbital mechanics is crucial because these celestial movements drive the tidal heating that keeps its ocean liquid, create the stresses that crack and reshape its surface, and even influence where and when potential plumes might erupt. This gravitational ballet, performed continuously for billions of years, has made Europa what it is today, a potentially habitable world in an unlikely location. Europa orbits Jupiter at an average distance of about 417,000 miles, placing it well within the giant planet's powerful gravitational influence. This orbit takes Europa approximately 3.5 Earth days to complete, during which the Moon travels more than 1.5 million miles through space. But this seemingly simple orbit hides layers of complexity that make Europa's motion one of the most interesting examples of celestial mechanics in our solar system. The key to understanding Europa's unique situation lies in its relationship with its neighbouring moons, particularly Io and Ganymede. These three moons are locked in what astronomers call a Laplace resonance, named after the French mathematician Pierre-Simon Laplace, who first described such relationships. For every 4 orbits that Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This isn't approximately true. It's precise to an extraordinary degree, maintained by the mutual gravitational influences of the moons themselves. This resonance didn't happen by chance. Over millions of years, the moons gradually migrated into this configuration through a process called tidal evolution. Once locked into the resonance, they've remained there, unable to escape this gravitational embrace. The resonance is self-maintaining. If one moon starts to drift slightly from its prescribed orbit, the gravitational pulls of the others bring it back into line. It's a natural example of what engineers would call a feedback control system, but one that operates on a planetary scale. The importance of this resonance cannot be overstated when it comes to Europa's geology and potential habitability. If Europa orbited Jupiter alone, tidal forces would have long ago circularized its orbit, eliminating the eccentricity that drives tidal heating. The moon would have frozen solid billions of years ago. But the resonance with Io and Ganymede prevents this circularization, maintaining Europa's orbital eccentricity at about 0.009. Small but crucial, this eccentricity means that Europa's distance from Jupiter varies by about 7,000 miles during each orbit. When Europa is closest to Jupiter, at what we call perihove, it experiences stronger gravitational pull than when it's farthest away at apogee. This varying gravitational force causes Europa to stretch and compress like a stress ball being repeatedly squeezed. The solid surface can rise and fall by as much as 30 meters, nearly 100 feet, during each orbit. To understand the scale of these tidal forces, imagine standing on Europa's surface. Over the course of about 42 hours, the ground beneath your feet would rise and fall by the height of a 10-story building. This happens not through any volcanic or seismic activity, but purely through the gravitational stretching of the entire moon. These tidal bulges move around Europa as it rotates, creating the stresses that crack the ice and generate the heat that maintains the ocean. The pattern of tidal stress on Europa is complex and varies depending on location and time. At any given point on the surface, the stress changes in both magnitude and direction as Europa orbits Jupiter. These changing stresses create a pattern of tension and compression that can open existing cracks, close others, and create new fractures in the ice. The lineae we see on Europa's surface are essentially a record of these tidal stresses accumulated over millions of years. Europa's rotation adds another layer of complexity to the tidal picture. Like most moons in the solar system, Europa is tidally locked to Jupiter, meaning it rotates once on its axis for every orbit around the planet. This synchronous rotation ensures that the same hemisphere of Europa always faces Jupiter, just as the same side of our moon always faces Earth. The subjovian point, the spot on Europa directly beneath Jupiter, experiences different tidal stresses than the anti-Jovian point on the opposite side. But there's evidence that Europa's ice shell might not be perfectly locked to the interior. Some scientists believe the ice shell could be rotating slightly faster than the rocky interior, a phenomenon called non-synchronous rotation. If true, this would mean the ice shell gradually shifts position relative to the interior over thousands or millions of years. This could explain some of the surface features that don't quite match predicted tidal stress patterns and would have important implications for how material is exchanged between the ocean and surface. The tidal heating generated by Europa's orbital dynamics is the key to its potential habitability. As Europa flexes during each orbit, friction within the ice and at the boundaries between different layers generates heat. The amount of heat generated depends on the internal structure. A completely solid body would generate less heat than one with liquid layers that can deform more easily. Current estimates suggest Europa generates between 10 and 100 terawatts of heat through tidal friction. This heat flow is not uniform across Europa. Models suggest that tidal heating is most intense near the poles and least intense at the equator, though this pattern could be modified by variations in ice shell thickness or ocean currents. The distribution of heat affects everything from the thickness of the ice shell to the location of potential plumes to the circulation patterns in the ocean below. Europa's position within Jupiter's magnetosphere adds another dimension to its orbital environment. As Europa orbits Jupiter, it plows through the giant planet's magnetic field and the charged particles trapped within it. This creates what's essentially a wind of high-energy particles constantly bombarding Europa's surface. The interaction between Europa and Jupiter's magnetosphere creates a wake in the magnetic field, like the wake behind a boat, and generates auroral emissions on Jupiter itself. The radiation environment around Europa is one of the most intense in the solar system. The charged particles trapped in Jupiter's magnetic field are accelerated to near the speed of light, creating a radiation environment that would be lethal to humans in minutes. This radiation doesn't just affect the surface chemistry of Europa, it also creates a tenuous atmosphere through a process called sputtering, where high-energy particles knock water molecules off the surface and into space. Europa's orbital period of 3.5 days means it experiences about 104 days per Earth year. But because Jupiter's year is nearly 12 Earth years long, Europa experiences seasonal variations on much longer timescales. These seasonal changes are subtle because Jupiter's axial tilt is only about 3 degrees, but they might influence long-term climate patterns or the timing of geological events. The gravitational influence of the other Galilean moons extends beyond just maintaining Europa's orbital eccentricity. When Europa and another moon are on the same side of Jupiter, their combined gravitational effect on each other is different than when they're on opposite sides. These periodic alignments create additional variations in the tidal stresses Europa experiences, potentially triggering events like plume eruptions or the formation of new cracks. Europa's orbit also determines its observability from Earth and the design of missions to explore it. Because Europa orbits relatively close to Jupiter, it's often lost in the planet's glare when viewed from Earth. The best times to observe Europa are when it's at greatest elongation, farthest from Jupiter in the sky. For spacecraft missions, Europa's orbit determines the trajectory needed to reach it, and the radiation exposure the spacecraft will experience. The long-term stability of Europa's orbit is remarkable. Despite the complex gravitational interactions with Jupiter and the other moons, Europa's orbit has remained stable for billions of years. Computer simulations suggest this stability will continue for billions of years into the future, ensuring that the conditions that might support life will persist. The measurement of Europa's orbital parameters has been refined over centuries of observation. From Galileo's first estimates of the orbital period to modern measurements, accurate to fractions of a second, each improvement in precision has revealed new details about Europa's interior structure and dynamics. Tiny variations in Europa's orbit, measured by tracking spacecraft flying past, provide information about the Moon's internal mass distribution and the presence of the subsurface ocean. The libration of Europa, a slight wobbling in its rotation, provides another clue about its interior. If Europa were solid throughout, its libration would be smaller than what we observe. The measured libration is consistent with a rigid ice shell floating on a liquid ocean, able to wobble slightly independently of the rocky core. This is one of several independent lines of evidence, all pointing to the existence of the subsurface ocean. Europa's position in the Jovian system also affects its interaction with the solar wind. While Jupiter's magnetosphere usually shields Europa from the solar wind, there are times when the magnetosphere is compressed and Europa finds itself exposed. These events, while rare, could affect Europa's thin atmosphere and surface chemistry, potentially leaving detectable traces in the surface ice. The question of whether life exists in Europa's dark ocean represents one of the most profound scientific inquiries of our time. This search for life beyond Earth has transformed Europa from an interesting moon into a priority destination for astrobiology, driving mission planning, technological development, and our understanding of what makes a world habitable. The possibility that microbial life, or perhaps even more complex organisms, might exist in Europa's ocean has captured the imagination of scientists and the public alike, fundamentally changing how we think about life in the universe. When we consider the possibility of life on Europa, we're guided by our understanding of life on Earth, the only example we have so far. Life as we know it requires several basic ingredients: liquid water, chemical building blocks like carbon and nitrogen, an energy source, and sufficient time for life to develop. Europa appears to have all of these ingredients, making it one of the most promising places in our solar system to search for life beyond Earth. The presence of liquid water on Europa is now well established through multiple lines of evidence. But it's not just the presence of water that makes Europa interesting. It's the longevity and stability of that ocean. Europa's ocean has likely existed for most of the Moon's 4.5 billion year history, providing a stable environment where life could potentially arise and evolve. On Earth, life appeared relatively quickly once conditions were suitable, possibly within a few 100 million years of the planet's formation. Europa has had 10 times longer. The chemical ingredients for life are also likely present on Europa. The Moon formed from the same disk of material that created Jupiter and the other Galilean satellites, which would have included organic compounds. Molecules containing carbon that serve as the building blocks of life. Comets and asteroids impacting Europa over billions of years would have delivered additional organic material. And radiation chemistry on the surface creates new organic compounds, some of which might find their way into the ocean. Energy is perhaps the most critical requirement for life, and Europa offers several potential energy sources. The most obvious is chemical energy from the reaction between different compounds. On Earth, many microorganisms derive energy from chemical reactions, a process called chemosynthesis. For example, some bacteria use the reaction between hydrogen sulfide and oxygen to power their metabolism. Similar reactions could occur in Europa's ocean, particularly if there are hydrothermal vents on the seafloor. The radiation environment at Europa's surface, while hostile to life as we know it, creates chemical disequilibrium that could serve as an energy source. Radiation splits water molecules into hydrogen and oxygen. The hydrogen escapes to space, but the oxygen and other radiation products could potentially make their way into the ocean, providing oxidants that life could use for energy. It's a harsh irony that the same radiation that would quickly kill any Earth life on Europa's surface might help power life in the ocean below. If hydrothermal vents exist on Europa's ocean floor, they would be game changers for the possibility of life. On Earth, hydrothermal vents support thriving ecosystems completely independent of sunlight. The chemical energy available at these vents, from reactions between seawater and hot rock, supports complex food webs starting with chemosynthetic bacteria. Similar vents on Europa could provide both the energy and the chemical building blocks necessary for life. The darkness of Europa's ocean, while eliminating photosynthesis as an energy source, isn't necessarily a barrier to life. Earth's deep oceans are also perpetually dark, yet they teem with life. Many organisms on Earth generate their own light through bioluminescence, using it for communication, hunting, or defense. If life exists in Europa's ocean, it might have evolved similar adaptations to the darkness. The pressure in Europa's ocean, while extreme by surface standards, is within the range where Earth life thrives. At the top of Europa's ocean, the pressure would be similar to Earth's deep ocean trenches, where we found diverse ecosystems. Life on Earth has proven remarkably adaptable to pressure, with some organisms able to survive pressures that would instantly kill surface dwellers. The temperature of Europa's ocean is also within the range of habitability. While cold by Earth standards, probably ranging from about 28 to 40 degrees Fahrenheit, these temperatures are well within the range where Earth life thrives. Psychrophilic or cold-loving organisms on Earth can grow at temperatures below the freezing point of pure water, taking advantage of salts that lower the freezing point. The potential for life on Europa isn't just speculation. It's based on our expanding understanding of life's limits on Earth. Everywhere we've looked on Earth where there's liquid water, we've found life, from the driest deserts to the deepest ocean trenches, from boiling hot springs to ice-covered Antarctic lakes. These extremophiles organisms that thrive in extreme conditions have expanded our concept of habitability. One of the most relevant Earth analogues for Europa's ocean might be Lake Vostok in Antarctica. This lake has been sealed beneath more than 2 miles of ice for millions of years, cut off from the surface and existing in perpetual darkness. Yet when scientists finally sampled Lake Vostok's water, they found evidence of microbial life. If life can persist in Lake Vostok, it might also exist in Europa's much larger and potentially more hospitable ocean. The discovery of ecosystems around Earth's hydrothermal vents in the late 1970s revolutionized our understanding of life's possibilities. Before this discovery, scientists believed all ecosystems ultimately depended on sunlight through photosynthesis. The vent ecosystems proved that life could thrive on chemical energy alone, opening the possibility for life in places like Europa where sunlight never penetrates. Recent discoveries have found life in even more extreme Earth environments that serve as analogues for Europa. Microorganisms have been found living in solid rock miles beneath Earth's surface, deriving energy from chemical reactions between water and rock. Others survive in highly acidic or alkaline environments, in water with extreme salt concentrations, and in areas with radiation levels that would kill most organisms. The type of life that might exist on Europa is a subject of much speculation and scientific modelling. Most scientists expect that if life exists, it would be microbial, similar to bacteria or archaea on Earth. These simple organisms could form the base of a food web, possibly supporting more complex single-celled organisms. The possibility of multicellular life is more speculative, but not impossible, especially if Europa's ocean has been stable for billions of years. Some scientists have speculated about what adaptations Europa life might have evolved. Without sunlight, any complex organisms would need to navigate and find food in complete darkness. They might use echolocation like Earth's dolphins, or chemical sensing like many deep-sea organisms. If bioluminescence evolved, it could create a spectacular light show in the darkness, with organisms using light for communication or to attract prey. The search for biosignatures, signs of life that could be detected by spacecraft, is a major focus of Europa research. These biosignatures could take many forms. Chemical biosignatures might include unusual ratios of isotopes, complex organic molecules, or waste products of metabolism. Physical biosignatures could include structures created by life, like the stromatolites created by ancient bacteria on Earth. One of the most exciting possibilities for detecting life on Europa is through the analysis of plume material. If the observed plumes are real, and if they're carrying ocean material into space, they could provide a way to sample the ocean without drilling through miles of ice. A spacecraft flying through a plume could analyze its composition, looking for organic molecules, cells, or other signs of life. The Europa Clipper mission, scheduled to launch in the 2020s, is designed specifically to assess Europa's habitability. While not a life detection mission per se, Europa Clipper will study the ocean's composition, the ice shell structure, and the geology of the surface. It will look for places where ocean material might be accessible and identify the most promising sites for future landers. Future missions might include landers that could directly sample Europa's surface, looking for biosignatures in areas where ocean material has recently emerged. More ambitious concepts include robots that could melt through the ice shell to directly explore the ocean, though such missions face enormous technical challenges. The ice shell is miles thick, the environment is bathed in radiation, and maintaining communication through the ice would be difficult. The planetary protection protocols for Europa missions are stringent, reflecting both the Moon's potential for harbouring life and the risk of contamination from Earth. Spacecraft are carefully sterilized to prevent Earth microorganisms from contaminating Europa. These protocols are particularly strict for any mission that might contact the ocean or recently exposed ocean material. The discovery of life on Europa would have profound implications far beyond biology. It would mean that life arose independently, at least twice in our solar system, suggesting that life might be common throughout the universe. If Europa life had a different biochemistry than Earth life, it would show that life can take forms we haven't imagined. Even if Europa life were similar to Earth life, it would raise questions about whether life can spread between worlds. The search for life on Europa also raises philosophical and ethical questions. If we find life, how do we study it without harming it? Do we have the right to explore a world that might harbour life? How would the discovery change our view of our place in the universe? These questions are being actively discussed by scientists, ethicists, and policymakers as we prepare for the possibility of finding life beyond Earth. The absence of life on Europa would also be scientifically valuable, though perhaps disappointing. It would help us understand the limits of habitability and might indicate that the origin of life requires conditions more specific than just water, chemicals, and energy. It could help us refine our search for life elsewhere in the universe. Current research on Europa's habitability involves laboratory experiments, computer modelling, and studies of Earth analogues. Scientists are recreating Europa's ocean conditions in laboratories, testing whether Earth organisms could survive and whether prebiotic chemistry could lead to life. Computer models simulate ocean circulation, chemical evolution, and potential ecosystems. Field studies in extreme Earth environments help us understand what kinds of life might be possible on Europa. The exploration of Europa represents one of the most ambitious and challenging endeavours in planetary science, a multi-decade effort that has transformed our understanding of this remarkable moon from a point of light in Galileo's telescope to a world we now know harbours a vast ocean beneath its icy shell. Each mission to the Jovian system has built upon the discoveries of its predecessors, gradually unveiling Europa's secrets while raising new questions that drive future exploration. The story of these missions is one of technological innovation, scientific discovery, and human determination to understand worlds beyond our own. The exploration of Europa represents one of the most ambitious and challenging endeavours in planetary science, a multi-decade effort that has transformed our understanding of this remarkable moon from a point of light in Galileo's telescope to a world we now know harbours a vast ocean beneath its icy shell. Each mission to the Jovian system has built upon the discoveries of its predecessors, gradually unveiling Europa's secrets while raising new questions that drive future exploration. The story of these missions is one of technological innovation, scientific discovery, and human determination to understand worlds beyond our own. The first spacecraft to visit Europa were Pioneer 10 and Pioneer 11, launched in 1972 and 1973, respectively. These missions were primarily designed to study Jupiter itself, but they provided humanity's first close-up glimpses of the Galilean moons. Pioneer 10 flew past Jupiter in December 1973, passing within about 320,000 miles of Europa. These materials appeared to be salts, possibly including magnesium sulfate and sodium chloride, that might have come from the ocean below. This provided a potential window into the ocean's composition and chemistry, crucial information for assessing Europa's potential habitability. The Galileo mission also discovered that Europa has a very thin atmosphere, or exosphere, composed primarily of molecular oxygen. This oxygen is produced when charged particles from Jupiter's magnetosphere strike water molecules on Europa's surface, splitting them apart. While this atmosphere is far too thin to breathe or to support life as we know it, its existence tells us about the dynamic processes occurring at Europa's surface. Despite its successes, the Galileo mission also faced significant challenges that limited what it could achieve. The spacecraft's main antenna failed to deploy properly, drastically reducing the rate at which data could be transmitted back to Earth. This meant that many fewer images could be taken than originally planned, and difficult decisions had to be made about which observations to prioritize. Additionally, the intense radiation environment around Europa gradually degraded Galileo's electronics, limiting the number of close flybys that could be safely performed. The Galileo mission ended in September 2003, when the spacecraft was deliberately crashed into Jupiter to avoid any possibility of contaminating Europa with Earth microorganisms. By that time, Galileo had revolutionized our understanding of Europa, establishing it as one of the most promising places in the solar system to search for life beyond Earth. The mission's discoveries drove the development of future missions specifically designed to study Europa in even greater detail. Following Galileo, several spacecraft have provided additional observations of Europa while on their way to other destinations or while studying Jupiter. The Cassini spacecraft, primarily designed to study Saturn, flew past Jupiter in 2000 and provided valuable observations of Europa and the other Galilean moons. The New Horizons mission, on its way to Pluto, also flew past Jupiter in 2007 and captured images of Europa, including observations of what might have been a volcanic plume on Io affecting Europa's thin atmosphere. The Hubble Space Telescope has played a crucial role in Europa exploration, despite never leaving Earth orbit. In 2012, Hubble detected what appeared to be water vapor plumes erupting from Europa's south polar region, potentially shooting material up to 120 miles above the surface. These observations, while difficult and at the limit of Hubble's capabilities, suggested that Europa might be venting material from its subsurface ocean directly into space, similar to the plumes discovered on Saturn's moon Enceladus. Subsequent Hubble observations have provided additional evidence for plumes, though they appear to be intermittent and difficult to predict. If these plumes are real, and if they contain ocean material, they could provide a way to sample Europa's ocean without having to land on the surface or drill through the ice. This possibility has significantly influenced the design of future Europa missions. The Juno mission, currently orbiting Jupiter, has provided new insights into the Jovian system that indirectly inform our understanding of Europa. While Juno's primary mission focuses on Jupiter itself, its observations of the planet's magnetic field, radiation environment, and gravitational field provide context for understanding Europa's environment. Juno has also captured distant images of Europa, contributing to our understanding of the Moon's large-scale properties. Ground-based observations have continued to play an important role in Europa exploration. Advanced telescopes like the Keck Observatory and the Very Large Telescope have used adaptive optics to achieve unprecedented resolution from Earth, allowing scientists to study Europa's surface composition and search for changes over time. Radio telescopes have been used to study Europa's interaction with Jupiter's magnetosphere, while infrared observations have provided information about surface temperatures and composition. The James Webb Space Telescope, launched in 2021, has opened new windows for studying Europa from afar. Its powerful infrared instruments can detect heat from Europa's surface and potentially identify the composition of any plumes. Webb's observations complement those from spacecraft, providing a different perspective and the ability to monitor Europa over extended periods. Looking at the cumulative results of all these missions and observations, we can see how our understanding of Europa has evolved from speculation to scientific certainty about key features like the subsurface ocean. Each mission has answered some questions while raising new ones, driving the development of ever more sophisticated missions. The progression from Pioneer's first fuzzy images to Galileo's detailed mapping to Hubble's plume detections represents one of the great success stories in planetary exploration. The future of Europa exploration promises to be even more exciting than its past, with multiple missions in development that will revolutionize our understanding of this ocean world. These upcoming missions represent the culmination of decades of technological development and scientific planning, designed to answer the fundamental questions about Europa's habitability and the potential for life in its hidden ocean. From orbiting spacecraft as surface landers to concepts for submarines that could explore the ocean directly, the next few decades will see an unprecedented assault on Europa's mysteries. The Europa Clipper mission, NASA's next flagship mission to Europa, is currently under construction and scheduled for launch in October 2024. This sophisticated spacecraft represents the most ambitious mission to Europa ever undertaken, specifically designed to determine whether Europa's ocean could harbour life. Unlike previous missions that included Europa as one of several targets, Europa Clipper is entirely focused on this one fascinating moon, with every instrument and observation planned to maximize our understanding of its habitability. Europa Clipper will not orbit Europa directly due to the intense radiation environment. Instead, it will orbit Jupiter and make nearly 50 close flybys of Europa over the course of its mission, each one carefully planned to observe different regions and phenomena. This approach allows the spacecraft to spend most of its time outside the worst of Jupiter's radiation belts, extending its operational lifetime while still achieving comprehensive coverage of Europa. The spacecraft carries 9 sophisticated scientific instruments, each designed to address specific questions about Europa. The Europa imaging system will capture images of Europa's surface with resolution as fine as 50 centimeters per pixel in some areas, revealing details smaller than a desk. These images will help scientists understand the geological processes shaping Europa's surface and identify the most promising sites for future landers. The Europa Thermal Emission Imaging System will map Europa's surface temperatures, looking for warm spots that might indicate recent geological activity or places where the ice shell is particularly thin. This thermal mapping could identify active regions where ocean material might be accessible to future missions, or where plumes might originate. One of Europa Clipper's most important instruments is its ice-penetrating radar, called REASON, which stands for Radar for Europa Assessment and Sounding Ocean to Near Surface. This radar will peer beneath Europa's icy shell, potentially detecting the ocean interface and mapping variations in ice thickness. It might also detect lakes or pockets of water within the ice shell, revealing the three-dimensional structure of Europa's frozen carapace. The spacecraft's magnetometer will make precise measurements of Europa's induced magnetic field, building on Galileo's discoveries to better constrain the ocean's depth, extent, and salinity. By measuring the magnetic field during multiple flybys at different points in Europa's orbit, scientists will be able to create a detailed picture of the conducting layer, the ocean, within Europa. Europa Clipper's mass spectrometer will analyze the composition of Europa's extremely thin atmosphere and any particles ejected from the surface. If the spacecraft flies through a plume, this instrument could directly sample ocean material, analyzing its composition for organic molecules and other compounds relevant to habitability. Even without plumes, the mass spectrometer will provide crucial information about the chemistry occurring at Europa's surface. The mission also includes a dust detector that will analyze tiny particles orbiting near Europa. These particles, ejected from the surface by micrometeorite impacts or other processes, could provide another way to sample Europa's surface composition. The dust detector can determine the composition, speed, and direction of individual dust grains, building up a picture of the material being ejected from Europa. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, represents Europe's major contribution to outer solar system exploration. Launched in April 2023, JUICE will arrive at Jupiter in 2031 and spend at least 3 years studying Jupiter and its moons, with particular focus on Ganymede, Europa, and Callisto. While Europa is not JUICE's primary target, the mission will conduct 2 dedicated Europa flybys that will provide complementary observations to Europa Clipper. JUICE carries 10 scientific instruments designed to study the Galilean moons as a system, understanding how they formed and evolved together. During its Europa flybys, JUICE will use its ice-penetrating radar to study the ice shell, its visible and infrared imaging spectrometer to map surface composition, and its particle sensors to study Europa's interaction with Jupiter's magnetosphere. The coordination between JUICE and Europa Clipper, which will be operating in the Jupiter system at the same time, will provide an unprecedented opportunity for simultaneous observations from multiple perspectives. Beyond these approved missions, space agencies and scientists around the world are developing concepts for future Europa exploration. The Europa lander concept, studied extensively by NASA, would place a robotic lander on Europa's surface to directly search for signs of life. This mission would face enormous technical challenges, from surviving the radiation environment to landing safely on a surface we don't fully understand to operating in temperatures approaching -300 degrees Fahrenheit. The proposed Europa lander would carry a sophisticated suite of instruments designed specifically for astrobiology. These would include microscopes capable of identifying individual microbial cells, mass spectrometers that could detect complex organic molecules, and instruments to measure the chemical and physical properties of surface materials. The lander would use a sampling system to collect material from beneath the radiation-processed surface layer, where biosignatures would be better preserved. One of the most ambitious concepts for Europa exploration involves sending a probe through the ice shell to directly explore the ocean. Various designs have been proposed, from nuclear-powered probes that would melt their way through the ice to mechanical drills that would bore through. These cryobots, as they're called, would face extraordinary challenges, maintaining communication through miles of ice, surviving the pressure at the ocean interface, and operating autonomously in a completely unknown environment. Once a cryobot reached the ocean, it could deploy an autonomous underwater vehicle to explore. These submarine robots would need to navigate in complete darkness, potentially travelling miles from their entry point while maintaining the ability to return and communicate their findings. They would search for signs of life, study ocean chemistry, and potentially explore the ocean floor where hydrothermal vents might exist. The technological challenges of Europa exploration are driving innovations that could benefit many areas of science and technology. Radiation-hardened electronics developed for Europa missions could improve satellites operating in Earth's radiation belts. Autonomous navigation systems designed for Europa landers could enhance rovers on Mars or robots in Earth's oceans. Life detection instruments could revolutionize our ability to identify microorganisms in extreme environments on Earth. Communication with Europa missions presents unique challenges due to the vast distance and the fact that Europa is often hidden behind Jupiter from Earth's perspective. Future missions might use relay satellites orbiting Jupiter to maintain constant communication with surface assets. Advanced data compression and artificial intelligence could allow missions to prioritize the most important data for transmission when communication windows are limited. Power generation for the Europa missions is another significant challenge. Solar panels are marginally effective at Jupiter's distance from the Sun, receiving only about 4% of the sunlight that reaches Earth. Most future Europa missions will likely rely on radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity. For missions requiring more power, such as cryobots melting through the ice, nuclear fission reactors might be necessary. The planetary protection requirements for Europa missions are among the most stringent for any solar system destination. Because Europa potentially harbours life, we must be extremely careful not to contaminate it with Earth microorganisms. This requires extensive sterilisation procedures, careful material selection, and operational protocols to minimise contamination risk. Future missions that might contact the ocean or fresh ocean material will face even stricter requirements. International collaboration will be crucial for future Europa exploration. The enormous cost and complexity of these missions make them natural candidates for international partnerships. Already, Europa Clipper includes contributions from several countries, and future missions will likely involve even broader collaboration. This international approach not only shares costs, but also brings together the best expertise from around the world. The role of commercial space companies in Europa exploration is an emerging area of interest. While the extreme distance and harsh environment make commercial missions to Europa challenging, companies might contribute to technology, provide launch services, or develop innovative approaches to specific problems. As the commercial space industry matures, it could play an increasingly important role in outer solar system exploration. Sample return missions from Europa represent a long-term goal that would revolutionize our understanding of this moon. Bringing samples of Europa's ice and potentially ocean material back to Earth would allow analysis with instruments far more sophisticated than anything we could send to Europa. However, the technical challenges are immense, requiring not just collecting samples, but storing them, launching them from Europa's surface, and returning them to Earth, a journey that would take years. The development of artificial intelligence and machine learning is increasingly important for Europa missions. These technologies could enable spacecraft to identify interesting features autonomously, adapt their observation plans based on discoveries, and even conduct preliminary analysis of data before transmission to Earth. For underwater missions, AI would be essential for navigation and decision-making in the absence of real-time communication with Earth. New propulsion technologies could dramatically improve our ability to explore Europa. Nuclear electric propulsion could reduce travel time to Jupiter and provide more flexibility for orbital maneuvers. Breakthrough technologies like fusion rockets or even more exotic concepts could eventually make Europa more accessible, though these remain decades away from practical application. Europa does not stand alone as an ocean world in our solar system, but rather represents one member of an extraordinary family of moons and dwarf planets that harbour hidden seas beneath their icy surfaces. This remarkable discovery that liquid water oceans are actually common in the outer solar system has fundamentally transformed our understanding of planetary science and astrobiology. By examining Europa in the context of these other ocean worlds, we gain deeper insights into the processes that create and maintain these subsurface oceans, the diversity of potentially habitable environments in our solar system, and the implications for life beyond Earth. The discovery that multiple worlds in our solar system contain subsurface oceans was one of the most surprising revelations of the space age. When the Voyager spacecraft first flew through the outer solar system, scientists expected to find dead, frozen worlds. Instead, they discovered dynamic moons with geological activity, complex surfaces, and hints of hidden oceans. Today, we have strong evidence for subsurface oceans on at least 6 worlds, with hints of many more, suggesting that there is far more liquid water in the moons of the outer solar system than in all of Earth's oceans combined. Enceladus, Saturn's 6th largest moon, provides perhaps the most compelling comparison to Europa. Like Europa, Enceladus has a global ocean beneath an icy shell, maintained liquid by tidal heating. But Enceladus offers something Europa might not: guaranteed access to ocean material through its spectacular plumes. The Cassini spacecraft flew directly through these plumes multiple times, analysing water vapour, organic molecules, and tiny ice grains ejected from the ocean below. These measurements revealed that Enceladus's ocean is salty, contains organic compounds, and has a pH compatible with life as we know it. The differences between Europa and Enceladus are as instructive as their similarities. Enceladus is much smaller than Europa, with a diameter of only about 313 miles, compared to Europa's 1,940 miles. This size difference affects everything from the moon's internal structure to their ability to retain heat. Enceladus's ocean appears to be regional rather than global, concentrated beneath the South Polar region where the plumes originate. The ice shell on Enceladus is thought to be thinner than Europa's, perhaps only a few miles thick at the South Pole, making the ocean more accessible but potentially less stable over geological time. The plumes of Enceladus have provided unprecedented insights into an alien ocean's composition. Cassini detected molecular hydrogen in the plumes, a potential energy source for life that could be produced by hydrothermal reactions on the ocean floor. The spacecraft also found complex organic molecules, including some with masses above 200 atomic mass units, suggesting chemical complexity that could be relevant to the origin of life. These discoveries make Enceladus, like Europa, a prime target in the search for extraterrestrial life. Titan, Saturn's largest moon, and the second largest moon in the solar system, presents a different kind of ocean world. Beneath its thick atmosphere and hydrocarbon lakes lies another ocean, but one very different from Europa's or Enceladus's. Titan's subsurface ocean is likely buried beneath 30 to 60 miles of ice, and is thought to be extremely salty, possibly with ammonia acting as an antifreeze. The chemical environment of Titan's ocean would be exotic compared to Europa's, potentially limiting its habitability, but offering insights into the diversity of ocean chemistry possible in the outer solar system. What makes Titan unique among ocean worlds is that it also has surface liquids, lakes and seas of liquid methane and ethane. This creates the possibility of two completely different types of chemistry occurring simultaneously: water-based chemistry in the subsurface ocean and hydrocarbon chemistry on the surface. Some scientists have speculated about the possibility of exotic forms of life that might use liquid hydrocarbons instead of water as their solvent, though this remains highly speculative. Ganymede, Jupiter's largest moon and the largest moon in the solar system, harbours what might be the most complex ocean structure of all. Models suggest that Ganymede might have multiple ocean layers separated by different phases of ice. As pressure increases with depth, water ice transforms into denser phases with different properties. This could create a sandwich structure with alternating layers of liquid water and high-pressure ice, possibly including Ice 3, Ice V, and Ice VH. Each ocean layer might have different chemistry and different potential for habitability. Ganymede is also unique in being the only moon with its own magnetic field, generated by a liquid iron core like Earth's. This magnetic field creates a mini magnetosphere within Jupiter's massive magnetosphere, providing some protection from radiation. The interaction between Ganymede's ocean and its magnetic field is complex, with the ocean's electrical conductivity affecting the magnetic field structure. Understanding this interaction helps us interpret similar measurements at Europa and other ocean worlds. Callisto, the outermost of Jupiter's 4 large moons, presents a puzzle for ocean world science. Unlike Europa and Ganymede, Callisto appears to be only partially differentiated, with a mixture of rock and ice throughout much of its interior rather than distinct layers. Yet magnetic field measurements suggest it too might have a subsurface ocean, though probably deeper and less extensive than Europa's. Callisto's ancient, heavily cratered surface shows no signs of geological activity, making it a stark contrast to Europa's young, dynamic surface. The existence of an ocean within Callisto is surprising because the moon experiences much less tidal heating than Europa or Ganymede. This raises questions about how Callisto's ocean is maintained and whether other heat sources, such as radioactive decay or serpentinization reactions, might be more important than previously thought. Callisto demonstrates that subsurface oceans can exist even in seemingly geologically dead worlds. Moving beyond the gas giant moons, we find evidence for oceans in even more unexpected places. Ceres, the largest object in the asteroid belt and the only dwarf planet in the inner solar system, shows signs of a subsurface ocean, or at least regions of briny water beneath its surface. The Dawn spacecraft observed bright spots in some of Ceres's craters that appear to be salt deposits, possibly from briny water that reached the surface and sublimated away. This suggests that even relatively small worlds far from the giant planets can maintain liquid water in their interiors. Pluto, once considered the 9th planet and now classified as a dwarf planet, might also harbour a subsurface ocean. The New Horizons flyby in 2015 revealed a geologically young surface, with nitrogen glaciers, mountain ranges made of water ice, and vast plains that show no impact craters. Models suggest that a subsurface ocean could explain some of Pluto's geological features and its surprisingly spherical shape. If Pluto has an ocean despite being 40 times farther from the Sun than Earth, it would demonstrate that subsurface oceans are possible even in the coldest reaches of our solar system. Triton, Neptune's largest moon, is another potential ocean world. This captured Kuiper Belt object shows signs of geological activity, including nitrogen geysers observed by Voyager 2. Triton's retrograde orbit causes strong tidal heating that could maintain a subsurface ocean. Future missions to Neptune could determine whether Triton joins the growing list of confirmed ocean worlds. Several other moons show hints of possible subsurface oceans. Dione and Rhea, moons of Saturn, have shown evidence of geological activity and possible outgassing that might indicate subsurface liquid water. Ariel and Miranda, moons of Uranus, display surface features suggesting past geological activity that could have been driven by subsurface oceans. Even some of Jupiter's smaller moons might harbour pockets of liquid water beneath their surfaces. The diversity of these ocean worlds teaches us important lessons about planetary science. We've learned that tidal heating can maintain oceans in places where solar heating is negligible. We've discovered that ocean chemistry can vary dramatically, from relatively fresh water to brines so salty they challenge our understanding of habitability. We've seen that ice shells can range from a few miles to perhaps 100 miles thick, affecting how oceans interact with surface environments. Comparing the energy sources available in different ocean worlds helps us understand their potential for supporting life. Europa and Enceladus benefit from strong tidal heating due to their orbital resonances. Titan's ocean might be maintained by a combination of tidal heating and radioactive decay. Ceres might rely primarily on radioactive heating and chemical reactions. This diversity of energy sources expands the possible habitable zone in our solar system far beyond the traditional region where surface water can exist. The astrobiological potential varies significantly among ocean worlds. Europa and Enceladus are considered the most promising due to their likely hydrothermal activity, relatively accessible oceans, and chemical energy sources. Titan's ocean might be too cold and too salty for Earth-like life, but it could host exotic biochemistry. Ganymede's layered oceans might provide multiple habitable zones with different characteristics. Each world offers a different natural experiment in habitability. The study of ocean worlds has revealed that water-rock interactions are crucial for habitability. These interactions can produce chemical disequilibrium that life could exploit for energy, create organic molecules through serpentinization reactions, and buffer ocean chemistry to maintain habitable conditions. Worlds where the ocean is separated from the rocky core by high-pressure ice, like Titan and possibly Ganymede, might have limited water-rock interaction, potentially reducing their habitability. The discovery of so many ocean worlds has profound implications for astrobiology beyond our solar system. If subsurface oceans are common in our solar system, they might also be common around other stars. Exomoons orbiting giant planets in other solar systems could harbour subsurface oceans maintained by tidal heating, even if they orbit far from their star. This greatly expands the potential habitable zone around other stars and suggests that life might be more common in subsurface oceans than on Earth-like surfaces. Understanding ocean worlds as a class helps us prioritise exploration targets and develop appropriate technologies. Missions designed for one ocean world can often be adapted for others. Technologies developed for penetrating Europa's ice shell could be used on Enceladus or Titan. Instruments designed to detect biosignatures in one ocean could work in others. This synergy makes ocean world exploration more efficient and cost-effective. The comparative study of ocean worlds also helps us understand Earth better. Earth's oceans interact with the atmosphere and receive energy from the sun, making them very different from subsurface oceans. But studying how oceans behave under different conditions helps us understand fundamental oceanographic processes. The extreme conditions in some ocean worlds serve as natural laboratories for understanding water under conditions we can't easily replicate on Earth. As we draw near the end of our comprehensive journey through the story of Europa, it's worth taking a moment to reflect on what this remarkable moon represents in the grand context of cosmic exploration and our search for meaning in the universe. Europa is more than just another moon orbiting a distant planet. It has become a symbol of possibility, a beacon of hope in our quest to answer one of humanity's most profound questions. Are we alone in the universe? When we contemplate Europa floating in the darkness, 500 million miles from Earth, perpetually bathed in Jupiter's radiation, while harbouring an ocean that has existed in darkness for billions of years, we're confronting scales of time and space that challenge human comprehension. Yet through ingenuity, determination, and scientific methodology, we've managed to peer beneath Europa's icy shell and discover a world that might, just might, harbour life. This achievement represents one of the greatest intellectual accomplishments of our species. The ability to understand worlds we've never touched, to map oceans we've never seen, and to search for life in places our ancestors couldn't have imagined existed. The story of Europa is really multiple stories woven together into a narrative that spans centuries of human curiosity. It's the story of Galileo Galilei, shivering in the cold Italian night as he pointed his primitive telescope at Jupiter and discovered moons that challenged humanity's entire worldview. It's the story of generations of astronomers who patiently observed these distant points of light, slowly building our understanding one observation at a time. It's the story of the engineers who designed spacecraft capable of surviving journeys of hundreds of millions of miles and operating in radiation fields that would destroy ordinary electronics in seconds. But perhaps most importantly, it's the story of human curiosity and our relentless drive to understand our place in the cosmos. Every mission to Europa, every observation through a telescope, every computer model of its ocean represents humanity reaching out across the vast emptiness of space, seeking connection and understanding. We study Europa not because it offers immediate practical benefits, but because understanding this distant moon helps us understand ourselves and our cosmic context. The possibility of life in Europa's ocean forces us to reconsider what we mean by habitability. For most of human history, we've associated life with sunlit surfaces, warm temperatures, and conditions similar to those we experience on Earth. Europa challenges all these assumptions. Its ocean exists in perpetual darkness, at temperatures that would freeze water on Earth's surface, under pressures that would crush most surface life. Yet it might be teeming with organisms adapted to these extreme conditions. This expansion of our concept of habitability has profound implications for our search for life in the universe. If life can exist in Europa's dark ocean, then potentially habitable environments might be far more common than we ever imagined. The moons of gas giants previously dismissed as frozen wastelands might be the most common habitable worlds in the universe. This realization transforms our understanding of where and how to search for extraterrestrial life. Europa also teaches us about the importance of patience and persistence in scientific exploration. The journey from Galileo's first observation to our current understanding of Europa's subsurface ocean took 4 centuries. Each generation of scientists built upon the work of their predecessors, adding new pieces to the puzzle. The scientists who first speculated about Europa's ocean, based on Voyager data, knew they might not live to see their hypotheses confirmed. Yet they pursued the research anyway, driven by curiosity and the knowledge that they were contributing to humanity's greater understanding. The international nature of Europa exploration reflects the best of human cooperation. Scientists from dozens of countries have contributed to our understanding of Europa. Data from American, European, and other nations' spacecraft have been freely shared, analysed collaboratively, and discussed openly in the scientific literature. In an era often marked by division and conflict, Europa exploration stands as an example of what humanity can achieve when we work together toward common goals. The technological innovations driven by Europa exploration have benefits that extend far beyond planetary science. Radiation-hardened electronics developed for Jupiter missions improve satellite technology here at Earth. Autonomous navigation systems designed for Europa landers, advanced robotics, and artificial intelligence. Ice-penetrating technologies developed for Europa could help us explore Earth's polar regions and understand climate change. The challenges of Europa exploration push us to develop new capabilities that benefit all of humanity. The philosophical implications of potentially discovering life on Europa are staggering. For all of human history, life has been synonymous with Earth. Every living thing we've ever known, from the simplest bacteria to the most complex ecosystems, shares a common origin on our planet. The discovery of life on Europa would break this monopoly, demonstrating that life is not unique to Earth but can arise independently elsewhere in the universe. Such a discovery would fundamentally change our understanding of our place in the cosmos. If life arose independently on Europa, it would suggest that life might be common throughout the universe. We would have to reconsider our responsibilities as a spacefaring species. We would need to think carefully about how we explore other worlds, how we protect potential biospheres, and how we interact with any life we might discover. Even if Europa proves to be lifeless, the search itself is valuable. The absence of life in Europa's seemingly habitable ocean would teach us important lessons about the requirements for life. It might indicate that habitability requires more specific conditions than just water, energy, and chemical building blocks. It could help us refine our search for life elsewhere and better understand what makes Earth special. The study of Europa has already changed how we think about planetary science and astrobiology. The concept of ocean worlds, barely imagined a few decades ago, is now central to our understanding of the solar system. The possibility of subsurface biospheres has expanded our concept of the habitable zone. The discovery that tidal heating can maintain oceans for billions of years has revolutionized our understanding of planetary dynamics. Europa reminds us that the universe still holds countless mysteries waiting to be discovered. Despite all we've learned, fundamental questions remain unanswered. How thick is the ice shell? What is the exact composition of the ocean? Are there hydrothermal vents on the ocean floor? Is there life? Each answer we obtain raises new questions, driving continued exploration and discovery. The cultural impact of Europa extends beyond science into art, literature, and popular imagination. Science fiction writers have imagined countless scenarios for life in Europa's ocean, from microscopic organisms to complex ecosystems to intelligent beings. These creative explorations, while speculative, help us think about possibilities and prepare for discoveries that might challenge our expectations. Europa has become a touchstone for discussions about the future of space exploration. As we debate where to send our next missions, how to allocate limited resources, and what questions to prioritize, Europa consistently emerges as a compelling destination. It represents the perfect combination of scientific importance, technical challenge, and profound implications that justify the enormous effort required to explore it. The Moon has become a rallying point for those who believe that the search for life should be a primary driver of space exploration. Looking toward the future, Europa will likely play a central role in humanity's expansion into the outer solar system. If we establish a permanent human presence beyond Mars, the Jovian system with its resources and scientific treasures will be a natural destination. Europa's water could be a valuable resource for future space travellers, providing not just drinking water, but also oxygen for breathing and hydrogen for fuel. The Moon could become a refueling station, a research outpost, or even a home for future generations of humans living among the stars. The protection of Europa's potentially pristine environment raises important ethical questions that we're only beginning to grapple with. If life exists in Europa's ocean, do we have the right to study it? How do we balance scientific curiosity with the responsibility to preserve and protect? These questions aren't merely academic. They will shape the policies and protocols for future missions. The decisions we make about Europa could set precedents for how humanity interacts with life throughout the cosmos. The generational nature of Europa exploration connects us to both our past and our future. The scientists who first dreamed of exploring Europa's ocean have passed their vision to a new generation, who will in turn pass it to the next. Children today who are inspired by Europa's mysteries might be the ones who finally answer the question of whether life exists there. This continuity across generations represents one of humanity's greatest strengths, our ability to work toward goals that extend beyond individual lifetimes. Europa also serves as a reminder of how much our perspective has changed in a relatively short time. Just a century ago, the idea of liquid water oceans beyond Earth would have seemed like pure fantasy. Today, we know of multiple ocean worlds and are actively planning missions to explore them. This rapid expansion of knowledge gives us hope that the next century might bring discoveries we can't even imagine today. The technical challenges of exploring Europa push us to think creatively and ambitiously. How do we design a submarine for an alien ocean? How do we communicate through miles of ice? How do we search for life without contaminating the environment we're studying? These challenges require us to develop new technologies, new methodologies, and new ways of thinking. In solving these problems, we advance not just space exploration, but human capability in general. The search for life on Europa has helped unite different scientific disciplines in common purpose. Planetary scientists, astrobiologists, oceanographers, microbiologists, chemists, physicists, and engineers all contribute their expertise to understanding this distant moon. This interdisciplinary collaboration has led to new insights that wouldn't have been possible within traditional academic boundaries. Europa has become a catalyst for breaking down the barriers between different fields of study. The public fascination with Europa demonstrates humanity's deep-seated desire to know whether we're alone in the universe. When NASA announces new discoveries about Europa, millions of people around the world pay attention. School children learn about Europa's ocean in science class. Amateur astronomers point their telescopes at Jupiter, hoping to glimpse this distant moon. This widespread interest shows that Europa has captured not just scientific attention, but the human imagination. Europa's story is still being written. Every new observation, every computer model, every laboratory experiment adds another page to our understanding. The upcoming Europa Clipper mission will revolutionize our knowledge, but it will also raise new questions that will drive future exploration. Perhaps in your lifetime, we'll know whether Europa's ocean harbors life. Perhaps your children or grandchildren will be the ones to make that discovery. The story continues, and we're all part of it. As you drift off to sleep tonight, perhaps you'll dream of Europa's dark ocean, where alien currents flow through eternal night, where ice creaks and groans under Jupiter's relentless pull, where hydrothermal vents might glow dimly on the ocean floor, and where possibly life swims through the darkness. It's a dream based on science but filled with wonder, a dream that connects you to centuries of human curiosity and to futures we can barely imagine. Europa teaches us that the universe is far stranger and more wonderful than our ancestors could have imagined. It shows us that habitability isn't limited to warm, sunlit worlds like Earth. It demonstrates that even in the cold outer reaches of our solar system, dynamic processes can create environments where life might thrive. Most importantly, it reminds us that we've only begun to explore the cosmic ocean, and countless discoveries await those brave enough to seek them. The patience required for Europa exploration mirrors the patience life itself might need to evolve in that dark ocean. Just as life on Earth took hundreds of millions of years to develop from simple chemicals to complex organisms, our understanding of Europa has evolved slowly from points of light in primitive telescopes to detailed maps of an ice-covered ocean world. Both processes, the evolution of life and the evolution of understanding, require time, persistence, and the right conditions to flourish. When we consider Europa in the context of cosmic time, our urgent desire to know whether life exists there seems almost impatient. Europa's ocean has existed for billions of years and will likely exist for billions more. If life is there, it has been swimming in darkness since before complex life emerged on Earth's surface. It will still be there long after our sun has died and Earth has become uninhabitable. Yet we, ephemeral beings whose entire civilization spans just a few thousand years, are reaching across space to search for it. There's something beautifully audacious about that. The legacy of Europa exploration will extend far beyond whatever we discover there. The technologies we develop, the knowledge we gain, the international collaborations we forge, and the questions we ask will influence space exploration for generations to come. Future historians might mark the exploration of Europa as a turning point, the moment when humanity truly began to understand that oceans, and potentially life, are common throughout the cosmos. Europa reminds us that exploration is a fundamental part of being human. From our ancestors who left Africa to populate the globe, to the voyagers who crossed vast oceans, to the astronauts who walked on the moon, we have always been explorers. Europa represents the next frontier, not just in physical space, but in our understanding of life's possibilities. The same drive that once pushed us to cross unknown oceans now pushes us to explore alien ones. The story of Europa is ultimately a story of hope. Hope that we're not alone in the universe. Hope that life can thrive in places we never expected. Hope that humanity can overcome technical challenges that seem insurmountable. Hope that international cooperation can achieve what no single nation could accomplish alone. Hope that future generations will continue the quest for knowledge that defines our species. As we conclude this journey through the complete story of Europa, from its discovery by Galileo to the missions being planned today, we're left with more questions than answers. But that's as it should be. Science is not about having all the answers, but about asking better questions. Europa has taught us to ask whether life can exist without sunlight, whether oceans are common in the universe, whether the habitable zone extends far beyond what we once imagined. The next chapters in Europa's story will be written by the missions currently flying through space, by the scientists analysing data in laboratories around the world, by the engineers designing new technologies, and perhaps by you, inspired by the mysteries of this distant moon, to contribute your own verse to the great poem of exploration. Europa waits patiently in the darkness, keeping its secrets for now, but gradually revealing them to those persistent enough to seek them. Tonight, as you close your eyes and drift towards sleep, you carry with you the complete story of Europa, as we know it today. A story of discovery and wonder, of patience and persistence, of technology and imagination, of international cooperation and human ambition. But remember that this isn't an ending. It's merely a pause in an ongoing narrative that stretches from Galileo's first glimpse through his telescope to futures we can barely imagine, where humans might swim in Europa's ocean, or where we might finally know for certain that we are not alone. The universe is vast and full of wonders, but few capture our imagination quite like Europa. This small moon, locked in its eternal dance around Jupiter, has become a symbol of possibility in our search for life beyond Earth. Its hidden ocean calls to us across the void, challenging us to develop new technologies, to think in new ways and to dream of what might be swimming in that darkness. Whether Europa harbours life or stands as a beautiful but barren world, it has already changed us, expanded our horizons, and shown us that the cosmos is far more interesting than we ever dared to hope. Thank you for joining me on this extensive exploration of Europa, from its mythological namesake to its potential future as humanity's first confirmed discovery of extraterrestrial life. As you drift off to sleep, perhaps you'll dream of that distant ocean, dark and mysterious, waiting patiently for the day when we finally discover its secrets. Sweet dreams, and remember, somewhere out there, beneath miles of ice, an alien ocean moves through eternal night, keeping secrets that might change everything we thought we knew about life in the universe. If you enjoyed this journey through the complete story of Europa, please consider giving this video a like and subscribing to the channel for more in-depth explorations of our fascinating cosmos. Until next time, keep looking up, keep wondering, and keep dreaming about the mysteries that await us among the stars.